Let's take what we know about the graphs of simpler functions and apply it to this question of sketching graphs of polynomial functions. In general, as we sketch polynomial functions, we want to remember that the graphs are smooth and continuous. By smooth, we mean there are no sharp corners. Everything is a nice curve. And by continuous, we mean there are no breaks in the graph. We can combine our knowledge here of the end behavior of the graph, of the intercepts, maybe plotting some other values on the graph to provide a rough sketch of a polynomial function. So for our following example, let's first talk about end behavior. We said in the last video that the end behavior of the graph is determined solely by the leading term. In this case, it is x cubed. If you think about the graph of y equals x cubed, the y values go upward in this positive right quadrant, and they go downward in this negative left quadrant. So that's the end behavior of our graph. What happens in between? We can begin to piece it together if we have a few points. It's helpful to find the y-intercept and the x-intercepts. So for the y-intercept, we let x equals 0, and we solve for y. We're just plugging in x equals 0 to the function, and we get an output value of 8. So when x equals 0, y equals 8. We could mark that point on the graph, and we can go on to x-intercepts. For x-intercepts, we let y equal 0, and we solve for x. This tends to be a more challenging question. In this example, it looks like I can factor this expression by grouping to try solving for x. So let's pair the first two terms together and factor out x squared. And we pair the second two terms together and we factor out negative 4. And it happens to work out with factoring by grouping. We get x squared minus 4 times x minus 2 equals 0. Now x squared minus 4 factors even further. It's the difference of perfect squares. So we have x minus 2 times x plus 2 times x minus 2 equals 0. So that gives us a couple of solutions for x, either x equals 2 or x equals negative 2. That corresponds to the points 2, 0 and negative 2, 0. So we were able to factor this polynomial function and find the intercepts by factoring and solving the resulting equation. That is a more challenging question for polynomial functions in general, and in later videos we'll explore how we can find some of the zeros or the x-intercepts of these graphs when it doesn't work to factor by grouping. What other methods do we have at our disposal? So now I know a few points on this graph, and I can begin to get a rough shape of what this graph looks like. There's still a lot that I don't know, but I know that there's an intercept here. I know that there's a y-intercept here, another x-intercept here, and I know that the graph goes downward in this quadrant. This is a rough guess at what the sketch of this graph looks like. There are some things that are not exact here. For example, I don't know exactly where this turning point is without using calculus or technology such as a graphing calculator. There's also kind of a question here. How did I know just to touch the x-axis here and not to cross it? We'll address that in a later video. But I have a rough sketch of our graph in this case. Now I want to talk about one final topic, and that is we can describe the turning points of a graph. So a turning point is a point where the graph changes direction from increasing to decreasing, or vice versa. So the graph above has exactly 2 turning points. Both of them I have already circled. Those are the points where the graph changes from increasing to decreasing and then from decreasing to increasing. One of those turning points is 2, 0. The other one, I would need to use technology or some more advanced input of values to be able to tell you what this x and y value is. And just a general observation I'd like to make here is that the graph of a polynomial function of degree n has at most n minus 1 turning points and n x-intercepts. That is not a guarantee that there will be that many. Notice that we're saying there will be at most that many. So a polynomial function of degree 3, such as the one I graphed above, will have at most 2 turning points and at most 3 x-intercepts.